Imagine a computer that learns like a human. It interacts with its environment, it makes decisions, it learns from its mistakes. This is the exciting promise of deep reinforcement learning, or DRL. DRL is a powerful type of artificial intelligence. It combines the learning capabilities of reinforcement learning with the pattern recognition power of deep learning. This potent combination is revolutionizing AI. DRL systems are trained on vast amounts of data. They use this data to learn complex tasks. These tasks range from playing games to controlling robots. DRL is changing how we interact with technology. It's pushing the boundaries of what machines can do. In this essay, we'll embark on a journey to demystify deep reinforcement learning. We'll explore its key concepts, algorithms, and applications. We'll also delve into the challenges and future directions of this groundbreaking field. Join me as we unlock the secrets of DRL and explore its potential to shape the future of AI. Reinforcement learning, or RL, is a fundamental learning paradigm in AI. It mimics how humans and animals learn through trial and error. Imagine a child learning to ride a bike. They fall, they get up, and they adjust their balance until they can ride smoothly. In RL, an agent learns by interacting with an environment. The agent takes actions to achieve a specific goal. The environment provides rewards or penalties based on the agent's actions. The agent's objective is to learn a policy that maximizes its cumulative reward over time. Think of a dog learning a trick. The dog is the agent, the owner is the environment, the trick is the goal, treats are the rewards. Through trial and error, the dog learns to associate the desired behavior with the reward. RL is a powerful framework for training AI agents to solve complex problems. It has been successfully applied in various domains, including robotics, game playing, and control systems. Deep learning, a subfield of machine learning, is inspired by the structure and function of the human brain. At its core are artificial neural networks, complex structures that excel at recognizing patterns in data. These networks consist of interconnected nodes, or neurons, organized in layers. Each connection between neurons has a weight associated with it. These weights determine the strength of the connection. During training, the network adjusts these weights to learn the underlying patterns in the data. The more layers a network has, the deeper it is. This depth allows deep learning models to learn intricate representations of complex data. Imagine a deep learning model trained to recognize images of cats. By analyzing millions of cat images, the model learns to identify the distinctive features of cats, such as their ears, eyes, and fur patterns. Deep learning has revolutionized fields like computer vision, natural language processing, and speech recognition. Its ability to extract meaningful insights from vast data sets has paved the way for groundbreaking advancements in AI. Deep reinforcement learning, or DRL, emerges from the fusion of deep learning and reinforcement learning. This powerful synergy combines the pattern recognition prowess of deep learning with the decision-making capabilities of reinforcement learning. In DRL, deep neural networks are used to approximate the value functions or policies that guide the agent's actions. These networks can handle high-dimensional state and action spaces, making DRL suitable for complex problems with vast possibilities. Think of a DRL agent learning to play a video game. The agent perceives the game screen as its state. It uses a deep neural network to process this visual information and learn the game's rules and dynamics. Through trial and error, the agent learns to take actions that maximize its score. DRL has achieved remarkable success in recent years. It has enabled AI agents to surpass human performance in games like Go, chess, and Atari video games. DRL is also being applied in robotics, autonomous driving, and other fields where intelligent decision-making is crucial. Section 5: Q-learning and deep Q networks. Navigating the decision landscape. Q-learning is a fundamental algorithm in reinforcement learning. It focuses on learning a Q function that estimates the expected cumulative reward for taking a specific action in a given state. The agent uses this Q function to make decisions, choosing actions that maximize its expected return. Deep Q networks, or DQNs, take Q-learning to the next level by using deep neural networks to approximate the Q function. This allows DQNs to handle high-dimensional state spaces, making them suitable for complex problems like video games. Imagine a DQN agent learning to navigate a maze. The maze represents the environment. The agent's location is its state. Possible actions are moving up, down, left, or right. The agent receives a reward upon reaching the goal. DQNs have achieved impressive results in playing Atari games, demonstrating their ability to learn complex strategies from raw pixel data. They have paved the way for more sophisticated DRL algorithms. Section 6. Policy Gradient Methods, Mastering Actions Through Probabilities. Policy gradient methods offer an alternative approach to DRL. Instead of learning a value function like Q-learning, they directly learn a policy that maps states to actions. This policy is represented by a parameterized function, often a deep neural network. The agent learns by interacting with the environment and adjusting the parameters of its policy to maximize its expected cumulative reward. This is achieved by using gradient ascent, a mathematical technique for finding the maximum of a function. Imagine a policy gradient agent learning to control a robotic arm. The agent's policy determines the joint angles of the arm. The agent receives a reward for successfully grasping objects. Policy gradient methods are particularly effective in continuous action spaces, where the agent has an infinite number of possible actions to choose from. They have been successfully applied in robotics, control systems, and gameplaying. Section 7. Advanced Algorithms, Refining the Art of Learning. As DRL research progresses, new algorithms are constantly being developed to address the limitations of existing methods and push the boundaries of what's possible. Double DQN, or Double Deep Q Network, is an enhancement over the original DQN algorithm. It addresses the issue of overestimation bias in Q learning, leading to more stable and accurate learning. Proximal policy optimization, or PPO, is a popular policy gradient method known for its stability and efficiency. It constrains the policy updates to ensure that the new policy remains close to the old policy, preventing drastic changes that can destabilize learning. Actor-Critic methods combine elements of both value-based and policy-based methods. They use two neural networks, an actor network that learns the policy and a critic network that learns the value function. The actor and critic networks work together to improve the agent's performance. These advanced algorithms, along with others like Deep Deterministic Policy Gradient, or DDPG, and Trust Region Policy Optimization, or TRPO, are driving progress in DRL and enabling AI agents to tackle increasingly complex challenges. Section 8. Applications of Deep Reinforcement Learning, from Games to Reality. Deep reinforcement learning is no longer confined to the realm of research labs and video games. Its real-world applications are rapidly expanding, transforming industries, and shaping our future. In robotics, DRL is enabling robots to learn complex manipulation tasks, such as grasping objects, assembling products, and even performing surgery. DRL-powered robots are becoming increasingly dexterous and adaptable, paving the way for their wider adoption in manufacturing, healthcare, and other sectors. Autonomous driving is another field where DRL is poised to revolutionize transportation. DRL algorithms can learn to navigate complex road conditions, make real-time decisions, and interact safely with other vehicles and pedestrians. DRL-powered self-driving cars promise to enhance road safety, improve traffic flow, and reduce transportation costs. Beyond robotics and autonomous driving, DRL is finding applications in finance, healthcare, energy management, and personalized recommendations. Its ability to learn from data and optimize complex systems makes it a valuable tool in various domains. Section 9. Challenges and Limitations, Navigating the Uncharted Territory. Despite its remarkable achievements, deep reinforcement learning still faces several challenges and limitations that researchers are actively working to overcome. One major challenge is data efficiency. DRL algorithms often require massive amounts of training data, which can be time-consuming and expensive to collect. This is particularly problematic in real-world applications where data collection is limited or costly. Another challenge is generalization. DRL agents can struggle to generalize their learned behaviors to new unseen environments or tasks. This is because they often overfit to the specific training data, failing to learn the underlying principles that would allow them to adapt to different situations. Safety and robustness are also crucial concerns in DRL, especially in safety-critical applications like autonomous driving and healthcare. DRL agents need to be able to operate safely and reliably in complex, dynamic environments, even in the presence of uncertainties and unexpected events. Addressing these challenges is essential for unlocking the full potential of DRL and ensuring its safe and beneficial deployment in real-world applications. Section 10. Conclusion. Shaping the Future of Intelligent Systems. Deep reinforcement learning stands as a testament to the transformative power of AI. Its ability to learn complex behaviors from interactions with the environment has opened up new frontiers in artificial intelligence, enabling machines to solve problems that were once thought to be the exclusive domain of humans. From mastering games to controlling robots, DRL is rapidly expanding its reach, revolutionizing industries, and shaping our future. As researchers continue to refine DRL algorithms and address its challenges, we can expect even more groundbreaking applications in the years to come. DRL is not merely a technological advancement, it's a paradigm shift in how we think about intelligence and learning. By mimicking the trial and error learning process of humans and animals, DRL offers a glimpse into the future of intelligent systems, one where machines can learn, adapt, and evolve alongside us. As we venture further into the realm of deep reinforcement learning, we embark on an exciting journey of discovery, innovation, and endless possibilities.